Okay? So now let's go back and let's try to talk about and put into words what that picture can tell us and how this can relate to entropy. So we can say something about this. We have our particular system over here, and we're considering a fixed amount of an ideal gas. So N's constant, P's constant, V's constant, T's constant. The state or macro state of a system is defined by a given set of conditions. And we can define this set of conditions in any way that we want. We can say that we have an ideal gas, which means all the collisions between the molecules are going to be perfectly elastic. We can say that we have constant pressure, volume, and temperature, and a constant number of moles. From all those molecules that we showed, which we would call a macro state, we can have different, what we call microstates. So a given macro state can exist as a result of a large number of different microstates. And the question is, what are these microstates that make up and that combine together to form this macro state? And a microstate can be thought of as a snapshot of the system at a given time, and is different from moment to moment. So if we're going to look at how these molecules are interacting, we have all the molecules bouncing into each other and bouncing off of each other. If I hit pause on that screen at any given moment, all 30 of those molecules could have a different speed. We can put restrictions on what the speed of one of these molecules would be just so we can look at these different states. So the first set of states that we're going to look at is going to be what I'm going to call state A versus state B. We're going to put a given set of conditions on each of these states, and we can look at the overall relative energy of each of them. So, for example, we're going to take A and B, both consist of two particles with a total energy equal to 4 joules. So we have a total of 4 joules of energy. We can put different limitations on each of these states. State A, we're going to make the first particle equal to 2 joules of energy. If our overall system has an energy of 4 joules and particle 1 is at 2 joules of energy, what does particle 2's energy have to be? It also has to be 2 joules. And there's only one way that we can represent these two particles if one of them has to be 2 joules of energy. If, for instance, in state B, and I shouldn't say the first particle here, I should say one particle has to have an energy of 2 joules. For state B, we're going to say that one particle has to equal 3 joules of energy. So here's our energy scale again. One particle is going to be 3 joules of energy. The second particle then has to be 1 joule. So here's our particular energy diagram. So this is what we would call microstate number 1 for each of these macro states. But there's also another way that we can represent these two particles in state B. In state B, the first particle can now have an energy of 1 joule, and the second particle can have an energy of 3 joules. So this is a second microstate that will give us the same energy as the first microstate did. We're just flipping around particle 1 and particle 2. If these particles are identical and an ideal gas, we can have two ways of representing them in state B versus only one way of representing them in state A. We call these guys right here microstates. So in state A, we can say that W from our other equation is equal to 1. And in state B, our W is equal to 2. And we know that the entropy, which is S, is going to equal K times the natural log of W. So as W increases, our entropy is going to increase. So we can say that system B has more microstates that results in the same 4 joule macrostate. So since W for state A is greater than the W for state B, system B, or state B, has a greater entropy. And what we can say from this is that state B has more energetically equivalent ways to arrange the components, or has more energetically equivalent ways to arrange the components of the system. So this is going to lead to a more stable state. And a very, very important concept that we can take away from this is that the state with the highest entropy has the greatest number, or actually has the greatest dispersal of energy. Another way of saying this is that the energy can disperse out across a system. And we can look at different systems. The systems could be a combination of molecules. The system can be a molecule itself. And if you remember back from some of the chapters in Chapter 8 and Chapter 9, when we talk about Lewis structures and resonance structures, remember, resonance structures are structures that have the same energy, yet the electron distribution is spread evenly throughout that particular molecule. There's a term called resonance stabilization. This ties into the same exact concept that we look here with entropy. Because if I have resonance, that means I have two molecules that have the same energy. And in terms of the electrons, remember we talked about last chapter, electrons want to repel each other. So if we can somehow disperse that energy and that repulsion across an entire molecule rather than in a fixed space, we can result with a more stable structure. If you're lucky enough to go on to organic chemistry next year, you'll talk about resonance stabilization in great detail. And that has to do with the number of states that we're going to observe here. So we've taken this with a simple model where we're talking about how can we put two particular particles with energy restrictions on them. And what we're going to talk about next week is if I have a particular gas molecule and I have a container that I'm looking at, and I have 5 gas particles over here in this vessel, and it's connected to another vessel with an opening here, and I partition them off as separate containers, but then open them up and allow the gas particles to move over to the other side, what's the probability and what's the likelihood of having all 5 particles stay over here in the same container? Will they diffuse over to the other container? How many states can we look at? And how spontaneous would that happen? Okay? And we're going to look at spontaneity. So what I want to highly focus on and emphasize is make sure you read the first couple sections of Chapter 19 this weekend, because that'll help you get a leg up of what we're going to be talking about on Monday. So we'll pick up on Monday with more of this discussion.